Hello everyone. In the beginning of the class, let us see new announcements. Okay. So the first new announcement is May 19th, 2022. Class videos uploaded. Hello everyone. I have uploaded class videos of May 19, 2022 to YouTube. Their URLs are this, and this. Best regards, Wei Zhen. Okay, the second new announcement is please complete the teaching questionnaire for EMI course. Okay, what is an EMI course? Okay, it means that this course is taught in English. Hello everyone. As the semester draws to a close, I encourage you to complete the EMI course teaching questionnaire by June 5th, 2022. The results of the questionnaires will be used as a reference for teacher award applications, student counseling, and English proficiency improvement activities in the next semester. Okay, this is the teaching feedback questionnaire for EMI courses, student version. And this is the URL. Okay, and the questionnaire is in English. Okay, and this is the QR code. Next, it is 全英语授课教学回馈调查问卷学生版。And this is the URL, and the questionnaire is in Chinese. Okay, and this is the QR code. Best regards, Wei Zhen. Okay. Okay, the third new announcement is the handout of Chapter 2 has been updated. Version 2022-0524. Hello everyone. I have uploaded the latest version of the handout of Chapter 2 to eCourse 2 website. The location and the file name are eCourse 2 website, wireless communications and machine learning, course content, handouts, Chapter 2 handout 2022-0524.pdf. Best regards, Wei Zhen. Okay, next let us look at the progress of the last class. In the last class, we have taught to Chapter 2 handout, page 47. Problem 51 solution, Suprema. Okay, so please open the handout of Chapter 2 and search for page 47 and search for problem 51. Okay. So problem 51 asks what is maximum likelihood estimation. Okay, and we have taught to the Suprema. So where is the Suprema? Okay, let us search for it. Suprema. Okay. So for an open theta, okay, this is capital theta. What is capital theta? Let us review the definition of capital theta. Okay, here capital theta is called the parameter space, a finite dimensional subset of Euclidean space. Okay, for an open capital theta, the likelihood function may increase without ever reaching a supremum value. Okay, what is a supremum? Okay, let us we have introduced it before. Okay, you can search for the handout. Okay, then in figure 20 we have introduced the supremum, which is the least upper bound. Okay. In practice, it is often convenient to work with the natural logarithm of the likelihood function called the log likelihood. Okay. Small l of theta y is equal to natural log capital Ln of theta y. Okay. Do you remember what is small theta? Okay, let us review it. Okay, let us search for small theta. Okay, small theta is equal to theta 1, theta 2 to theta k transpose. Okay, so it is the parameters governing the joint distribution as a vector. Okay. Okay, small l of theta y. Okay, then what is y? Okay, let us review it. Okay, so the vector y is equal to y1, y2 to yn. Okay, it is the observed data sample. Okay, so this is equal to natural log of capital Ln of theta y. Okay, and capital Ln is the likelihood function. Okay, since the logarithm is a monotonic function, okay, more specifically, it is a monotonically increasing function. The maximum of small l of theta y occurs at the same value of theta as does the maximum of capital Ln. Okay, if small l of theta y is differentiable in capital theta, the necessary conditions for the occurrence of a maximum or a minimum are partial L over partial theta 1 is equal to 0. Partial L over partial theta 2 is equal to 0, and so on. Okay, finally, partial L over partial theta k is also equal to 0. Okay, known as the likelihood equations. For some models, these equations can be explicitly solved for theta hat. Okay, what is theta hat? Okay, let us review it. Okay, let us see the theta hat. Okay, theta hat is the values of the model parameters that maximize the likelihood function over the parameter space. That is this equation. Okay, theta hat, I should say small theta hat is equal to argument maximum. Small theta is in capital theta. L hat n of theta y. Okay. Okay, but in general, no closed form solution to the maximization problem is known or available. And an MLE, okay, here MLE means maximum likelihood estimation, can only be found via numerical optimization. Another problem is that in finite samples, there may exist multiple roots for the likelihood equations. Whether the identified root theta hat of the likelihood equations is indeed a local maximum depends on whether the matrix of second order partial and cross-partial derivatives, the so-called Hessian matrix. Okay, let us see the Hessian matrix. Okay, Hessian matrix H of theta hat is this matrix. Okay, it is a K by K matrix. Okay, in the first row, the first element is partial square L over partial theta 1 square, where theta is equal to theta hat. Okay. The second element is partial square L over partial theta 1 partial theta 2, where theta is equal to theta hat. Okay, and so on. The last element is partial square L over partial theta 1 partial theta k, where theta is equal to theta hat. Okay, in the second row, the first element is partial square L over partial theta 2 partial theta 1, where theta is equal to theta hat. The second element is partial square L over partial theta 2 square, where theta is equal to theta hat. Okay, and so on. Okay, and the last element is partial square L over partial theta 2 partial theta k, where theta is equal to theta hat. Okay, and so on. Finally, the last row. In the last row, the first element is partial square L over partial theta k partial theta 1, where theta is equal to theta hat. The second element is partial square L partial theta k partial theta 2, where theta is equal to theta hat. Okay, and so on. Finally, the last element is partial square L over partial theta k square, where theta is equal to theta hat. Is negative semi-definite at theta hat. We will introduce what is negative semi-definite later, as this indicates local concavity. Okay, I will also introduce what is concavity later. Okay, conveniently, most common probability distributions, in particular the exponential family. Okay, I will introduce what is exponential family later, are logarithmically concave. Okay, I will introduce what is logarithmically concave later. Okay, let us see an example. Okay, discrete distribution, finite parameter space. Suppose one wishes to determine just how biased an unfair coin is. Okay, what is an unfair coin? Okay. First, a fair coin means that when you toss the coin, the probability of head is equal to 1 second, and the probability of the tail is also equal to 1 second. Okay, it is a fair coin. Okay, so in contrast, an unfair coin means that when you toss this coin, the probability of head and the probability of tail are not equal. Okay, we call the probability of tossing a head P. The goal then becomes to determine P. Okay, suppose the coin is tossed 80 times. That is, the sample might be something like, okay, x1 is equal to h, where h means head. x2 is equal to t, where t is means tail, and so on. x80 is equal to t, and the count of the number of heads, okay, h is observed. Okay, the probability of tossing tails is 1 minus p, so here p is theta above, that is the parameter. Suppose the outcome is 49 heads and 31 tails, and suppose the coin was taken from a box containing 3 coins, one which gives heads with probability p, which is equal to 1/3, one which gives heads with probability p, okay, which is equal to 1 second, and another which gives heads with probability p, which is equal to 2/3. The coins have lost their labels, so which one it was is unknown. Using maximum likelihood estimation, the coin that has the largest likelihood can be found, given the data that were observed. Okay, so next, by using the probability mass function of the binomial distribution with sample size equal to 80, number success equal to 49, but for different values of p, the probability of success, the likelihood function defined below takes one of 3 values. Okay. First, the probability of h being equal to 49 given p is equal to 1/3, okay, which is equal to 80 chooses 49 times 1/3 to the power of 49 times 1 minus 1/3 to the power of 31, which is approximately 0.000, accurate to the 3rd digit after the decimal point. Okay, how do we calculate this value? Okay, we can write a MATLAB function, okay, like this. Okay, we write P1 is equal to n choose k. Okay, so this function will compute 80 choose 49, okay, and times 1/3 to the power of 49, and times 1 minus 1/3 to the power of 31. And let us press F5 to run this program. Okay, so we can see that there is some warning. Okay, 3 warnings. Okay, result may not be exact. Coefficient has a maximum relative error of 7.9936 to the power of minus 15. corresponding to absolute error 114378,346. Okay. So we have the three same warnings. Okay. So we can see that first P1 is equal to 0.0000, okay, which is approximately 0.000. Okay. Next, let us compute the conditional probability of H being equal to 49 given P is equal to 1/2. Okay, and this conditional probability is equal to 80 choose 49 times 1 second to the power of 49 times 1 minus 1 second to the power of 31, which is approximately 0.012, accurate to the third digit after the decimal point. Okay, so again we can use the MATLAB to compute. Here we named it P2, okay, which is equal to n choose k 8049 times 1 second to the power of 49 times times 1 minus 1 second to the power of 31. Okay, and after running this program, okay, the second is the answer 0.0118, so which is approximately 0.012. Okay, next let us compute the conditional probability of H being equal to 49. Okay, that is, there are 49 hits or 49 successes given P is equal to 2/3. Okay, so this conditional probability is equal to 80 chooses 49 times 2/3 to the power of 49 times 1 minus 2/3 to the power of 31, which is approximately 0.055. So how do we, so it is accurate to the third digit after the decimal point. So how do we get this value? Okay, again we write a MATLAB program. Okay, so P3 is equal to n choose k of 80 49 times 2/3 to the power of 49 times 1 minus 2/3 to the power of 31. And finally, we use the function DISP to display the value of P1, P2, P3. Okay, please note that we need to put P1, P2, and P3 into a pair of brackets, okay, to transform them into a vector. Okay, so finally the value of P3 is equal to, is approximately 0.0545. Okay, so it is approximately 0.055. Okay, the likelihood is maximized when P is equal to 2/3. Okay, let us see the results. Okay, so when P is equal to 2/3, this conditional probability is approximately 0.055, which is greater than this value and this value. Okay, so we can know that P is equal to 2/3, and so this is the maximum likelihood estimate for P. Okay. Okay, it is 25 minutes. Let us take a break.